Hello class, let us continue with lecture 12. I'm going to discuss on rotational energy levels for diatomic molecules and later on vibrational energy levels for the same diatomic molecules. Okay, let us recall what our Hamiltonian looks like in most of the system. So it was given by equation 1. Okay, so H your Hamiltonian, which is correspond to your kinetic energy and potential energy, and now you have an internal energy respect to having thermodynamic properties. And I wrote here R, so your R can be either 1 dimension, 2 dimensional or 3 dimensional, and your psi I here will correspond to the quantum states or your eigenfunctions. And usually you would like to have combinations of accessible quantum states. E here, remember this is always your eigenvalue. Alright. Also recall previously, let's say if we have a point particles, then the only possible motion is translation. So we can have say that previously if we are dealing with plus minus epsilon or this correspond to plus minus mu b, so it's correspond to translated energy. Okay, now we're going to look at system with more particles, okay, not just one. And for instance, we look at diatomic molecules, so we have two different atoms separated by some distance. So what is important over here, we are adding more parameter. Okay, now molecule rotate about its center of mass. Alright, so you can imagine if you can have a picture of molecule, later on you can just Google, alright, of Dewey molecules. For example, if you have carbon oxide, alright, so this is, you have two molecules, okay. And from QM you know that you can describe your consider two-dimensional problem with two variables of quantum states like this. So this is your cat vector. So it corresponds to L and M, or you can write in terms of function. Okay, so in terms of rotational kinetic energy, the eigenvalue is given by equation 2 here. So you have for each L, so your L can take 0, 1, 2, 3. Okay, no, your L can take one, at least one, because if your L 0, then this give you 0. Okay, so your L cannot be start with 0, so your L can start with 1, 2, blah blah blah. So everything here is coming from your quantum mechanics. Okay, and divide by 2i. So the rotational, we have an additional mu d square. Here is again your distance. All right. And the moment of inertia, your I is moment of inertia because of rotational properties. And m here is the reduced mass of the two atoms. That is mu, okay? So for m and L, it takes specific values. So m can take the least of that. So let's say if your L is 1, your m is minus 1, 1. So if your L is 2, your m is minus 2, minus 1, 0, 1, 2. So L will contribute to choices of your m. Let's say if you look into states. So if your L is 1, you have your m minus 1, 0, plus 1. So you have 3 sets of states with L equals to 1. So if you have L equals to 2, you have how many possible of your m? So you have 5 sets of states. Okay. So therefore, we have what we call degeneracy here. So all these is correspond to the degeneracy. So if your L is 1, you have G1, 3. So if your L is 2, you have 5, and so on and so forth. All right. So what we're going to do, and we are looking at the partial function for rotational motion. You know what is given by this. Remember, we are looking at, I'm using the Boltzmann probability distribution. So your partition functions will look like this. This comes from your degeneracy of the energy, and then multiply with the this part. Okay, so you just substitute your eigenvalue of rotational motion on this equation 3. After some analysis, and please do note, okay, the analysis is correspond to if you're looking at the very large of this. Okay, so in the exponential, so you have this form IKBT. Usually I think experimentalists, or if you want to plot something, you might want to consider having a very low, okay, smaller value of t, or a very high value. So in this case, if we want a very large of these parts, okay, which is giving your temperature getting low temperature, then you produce your free energy, entropy, and also heat capacity. So I did not put it in a, so this is like the total, the general formulation, but you can take it from the note. Your free energy is given by this. So your S is given by B here, and your C is that. All coming from just getting the correct partition. It should be partition function. Okay. All right. So what's next? For small of the term of in the exponential, then we want a very large temperature, which is this one. Okay. Then what you are producing, your partition function is given by this. Very lame. Let me write this down. Partition function. Okay, and then your free energy. Okay, you just substitute, and you get your entropy and also heat capacity. Okay, you can plot a figure from in this table. We look at the variations of heat capacity units in Boltzmann constant with temperature over the gas constant, okay, which is given by this formula. Okay, where your C is of course the speed of light, and B has dimension inverse length. So your B here, the dimension is L minus 1. Okay, so it's like inverse of the distance, and it has the dimensions of this. So you can look at if it's a very low of your T, your heat capacity become very small. Okay, compare if you, but there is some term here where your high, there's a value of T that give you a very high heat capacity, but after that, if you're adding more T, it becomes much more towards stationary. Okay, now the next part is on vibrational energy. So if we have rotational, so how many motions that we have? Translational for point particles, rotational. But another energy that one should consider if having diatomic molecule is vibrational energy. Okay, I would like to highlight here. The concept is very much similar from the previous. Okay, so potential is a different form. Okay, you can look up in your notes the potentials of your VR. Okay, there's some approximations been dealing with, but we look at the harmonic oscillator, the energy. Okay, the energy over here is approximately like a harmonic oscillator energy. So you can compute your partition function, your free energy, your entropy, and also your heat capacity. All right. For this vibrational case, the analysis is on respect to only on low temperature, and you get your Z is equivalent to this. Okay, this is the equation three double star. Then please look up at the figure in your text in the notes. Okay, for this for the variations of temperature. Okay, all right. Thank you, class. See you.